All right, in lesson 2, we're going to be looking at half of a square. So that's the title. So we're going to be investigating properties of diagonals of a square. So looking at, we know what diagonals are. Okay, so diagonals of a square is what we're going to be ending up getting into. This starts on page 132 in your workbook. So let's first start with this one, and let's just calculate the values of x and y. You've got a couple options. Definitely needing to start with Pythagorean theorem for finding one of them, and then it kind of opens up a couple options if you want to use similar triangles, seeing that we've got a 90-degree angle in each and a 29.7. Okay, so you could be looking at scale factor for the second one, or you could do Pythagorean theorem again. So pause the video, calculate those two values, then come back and check your work. All right, so Pythagorean theorem we have to start with. You can start with either one. I'm going to start with this one. Okay, locate the c value. So we do c squared equals a squared plus b squared. C is always the one across from the 90, so in this case it's x. So x squared equals, and then take the two legs. So 4 and 7, square those, add them together. So we get x squared equals 16 plus 49. So 4 times 4, 7 times 7. Add those together, and we get x squared equals 65. Square root both sides to undo that squared. So the square root and the square cancel, and we get x equals square root of 65, which is approximately 8.06. Then you could go ahead and figure out y. So you've got a couple options. Like I said, now that we know that this is 8.06, then we can take a look at scale factor, or you can do Pythagorean theorem again. So if you want to do Pythagorean theorem again, okay, you would locate the c value, and then you would set up Pythagorean theorem and do it very similar to the previous one. If you would like to do scale factor, then you're comparing two similar sides here. So two corresponding sides. So if I take a look here, I see that this one, okay, goes with this one. And then you would see that the factor that connects those, so how do you get 4 to 8 with multiplication, would be multiplying by 2. So the scale factor here is timesing by 2. So we take these small measurements, double them. So 4 times 2 is 8. 7 times 2 is 14. So we would take this hypotenuse and multiply it by 2 to get this one. So 8.06 times 2 gives us 16.12 for that y value. And you would see if you did the Pythagorean theorem that it would end up the same. So you'd get y squared equals 64 plus 196. Y squared equals 260. You would square root both sides, and you'd end up with y equals 16.12. All right, so taking a look at the next activity in your book, okay, draw a square that has side lengths of 1 centimeter. Okay, so you need to draw a square in there, make sure that it has 90-degree angles, and draw each of the sides with 1 centimeter. And then you're going to estimate the length of the diagonal. And your square doesn't have to be exact, because you're just going to actually be calculating, not measuring anything. So you can just draw a square, okay, and then label each side with a 1. And then we're going to estimate, okay, the length of the diagonal. So just guess, take a guess at how long you think this diagonal is. And then actually calculate the length of the diagonal. So calculate meaning to use mathematical formulas. So remember that you know that this one is a 1 centimeter side as well. And so we're looking for this diagonal. So you'd be doing Pythagorean theorem. So go ahead, pause the video and calculate that. All right, so we know that each side length of the square is 1 centimeter. That was given to us. So when we go to find the length of the diagonal, we'll be doing Pythagorean theorem. So the hypotenuse is that diagonal. So in this case, we don't know it. So x squared equals a squared, 1 squared, plus b squared, which is 1 squared as well. Okay, so each of those legs are 1. So we'd get x squared equals 1 plus 1. So x squared equals 2, square root both sides, and we'd get that x equals the square root 2. Okay, so you can leave it as square root 2. And then I'm also going to actually write that as its decimal, which is 1.41. So square root 2 or 1.41 is the length of the diagonal with a 1 centimeter square. All right, then if you are in class, you need to pick up a handout of some squares that you're actually going to measure with a ruler. Okay, so if you're in class, I need you to pick up the handout and you're going to measure these with rulers versus calculating. So you're actually going to just measure each of the sides. Okay, it's a square, so you just have to measure one and then measure the diagonal. And then I want you to do the ratio. Okay, and ratio means divide. And I want you to do the ratio of the diagonal to the side. Okay, so diagonal divided by side. If you are at home, okay, so if you are at home, then I want you to do what we did on the previous screen, okay, with the following 3 squares. Okay, so if you are at home, then you're going to take 3 squares. Okay, so just draw out 3 squares. And I want you to label the sides of this square, of the first square with 2's. Okay, so all the sides are 2. Okay, on this one, I want all the sides to be 3. And on this one, I want all the sides to be 4. So you can just write those in, and then you're going to calculate the length of the diagonals. Okay, so go ahead and do Pythagorean theorem there. You're actually going to calculate versus using a ruler. Okay, so go ahead and calculate the length of the diagonal using Pythagorean theorem. And then do the ratio again. So do diagonal divided by side length in each of those. Okay, so pause the video. If you're at home, finish that. If you are in class, okay, get finished up on the handout, actually measuring with a ruler. Okay, so now that you've measured the sides, if you are in class with the handout, so in triangle ABCD, you got the sides were about 5.7. The diagonal was about 8. So when you did 8 divided by 5.7, you should have gotten approximately 1.40. For EFGH, you got the side lengths to be 3.8, the diagonal to be 5.4, or approximately that. And I'm looking in centimeters. Okay, so then 5.4 divided by 3.8 should have gotten about 1.4. JKLM, you got the sides to be 8.5 centimeters, the diagonal to be 12. So when we did 12 divided by 8.5, should have gotten 1.4. Then those of you at home, okay, so when you did yours here, so you, after calculating with Pythagorean theorem, would have gotten this diagonal to be 2.8. So then 2.8 divided by 2, you'd have gotten 1.4. This diagonal with Pythagorean theorem, you would have gotten to be 4.2. 4.2 divided by 3, you would have gotten 1.4. This one with Pythagorean theorem, you would have gotten 5.6 or 5.7-ish. Okay, so then 5.7 divided by 4, you would have gotten 1.4. So hopefully you're seeing kind of a pattern here. So what pattern? So pause the video if you're in class and discuss this with your partner. Okay, and if you're at home, pause the video and just think about these. Then once you're done with that, push play and we'll talk about it. All right, so hopefully some patterns that you noticed was always that when we did the diagonal divided by the side in a square, it equals approximately, okay, so it wasn't exactly equal to, okay, but approximately equal to 1.4. And this actually is the square root of 2. Okay, so what conjecture did your group make? Okay, that the scale factor maybe, or the factor connecting the square's side and the diagonal. So if we take a side times 1.4, it would equal the diagonal. Maybe you came up with that. Or maybe the backwards version, a diagonal divided by 1.4 would equal the side. Or maybe you just said that the diagonal divided by the side always equals 1.4 in a square, but something like that. Okay, and why does that seem to always work? Okay, so think about why has to do with Pythagorean theorem, and we'll kind of get into a little bit of that. All right, so I want to do just a couple examples of simplifying radicals. We've talked about it a little bit, but we're going to get into it a little bit more. So just go ahead and do this with me on a scratch sheet of paper. So when we're simplifying radicals, or off to the side in your workbook is fine, you want to break down numbers into their prime factors, which means just divide them. And then if their factor divides further, keep going. So 4 times 10 is 40. 4 breaks down to 2 times 2. And then I circle the primes, so when they can't divide further. So then 10 is 2 times 5, so each of those are prime. So now a square root cancels a squared exponent. So what we want to do is group these together in 2's if possible, in doubles. Okay, so I have 2 2's here. So I'm going to take this 2 factor, and I had 2 of them. Okay, so 2 2's is 2 squared. Then I still had this other 2, and I had this other 5, but each of those I only had once. So now any squared factor, the square root will cancel it. So that's, you can rewrite it if you want to like this. So we can separate these radicals. So I can separate this one, and then I would leave these ones under that don't have a squared exponent. So now the square root of 2 squared is just a plain 2. And then these 2 stayed under the radical because they only have a 1 exponent. So then this is 2 square root 10. I would multiply those back together. So square root of 40 simplifies to 2 square root 10. So go ahead and try it with these 2 quick, and then come back to the video and see if you are doing it correct. So for 50, 50 would be 5 times 10. And then 10 is 2 times 5. So then when I put this back under, I want to pair the numbers up. So I see that I have 2 5s. So I'm going to put those 5s together as 5 squared, because that's 5 times 5. And then I also have this other factor of 2. So then when I break this up, I've got the square root of 5 squared, and I've got the square root of 2. So the square root will cancel the squared here, and we'll end up with 5 square root 2. So square root of 50 is the same as 5 square root of 2. So then 68, okay, maybe you're going to do 68 as 2 times 34. So you just do 68 divided by 2 if you didn't know that. So 68 divided by 2 is 34. So 2 times 34 equals 68. 34 also divides by 2, and it's 17. 17 is prime. So again, we'll get a 2 squared, and we'll get a 17. Remember, we want to put them in doubles because that's what cancels with the root. You noticed in this first one that I had 3 2's. I only put 2 of them together, and then I left that other one by itself. So then we've got 2 squared and 17. So square root of 2 squared is just 2. That's 17, stays under the radical. So square root of 68 is 2 square root 17. So what I want you to do is use this idea to generalize the pattern that we just looked at. Okay, so to look at these 3 examples and calculate using Pythagorean theorem. Okay, so remember, calculating, not measuring. Okay, so we want to calculate using mathematical formulas, not a ruler. Okay, the lengths of the unlabeled side. So in this case, you know, AC here, RQ and RP in here, these 2 legs. Okay, so I want you to kind of do these first 2 with Pythagorean theorem and then try to generalize it with this one. And when you're doing Pythagorean theorem, I want you to simplify the radical in the end. So you can pause the video, try each of those, and then come back. So in this first one, if we're looking for this, I'll just call it x. That's our c value. So we have x squared equals 3 squared plus 3 squared. So we have x squared equals 9 plus 9. So x squared equals 18. So we get x equals the square root of 18. So then if we break this down, instead of doing just the decimal form, okay, if we break it down, this is 2 times 9, and 9 is 3 times 3. So we get x equals, and I'm going to put those 3's together as 3 squared, and we still have this 2. So the square root will cancel the squared on the 3, and the 2 will stay under. So the exact form, non-decimal, of this is 3 square root 2. So remember, we talked about, okay, the diagonal in a square. So if we kind of extended this, that would be a square. Okay, this diagonal is always 1.4 times bigger than the side, or the square root of 2 times bigger. Okay, so if we take the side length and we multiply it by square root of 2, we get the diagonal. That's what just happened here. So if you calculated that with a decimal, 3 times 1.4, okay, so if we looked at 3 times 1.4, that would be 4.2. And if you calculated 3 times the square root of 2 in your calculator, so 3 square root 2 is about 4.2. So if we kind of think about this one as being a square also, okay, if we kind of could extend this, we know that this side will also be 14, since we see this 45-degree angle. That would mean this is 45, so the legs are the same. So now you could go through and do Pythagorean theorem again, or you could use your scale factor rule that you multiply the leg times the square root of 2. So 14 square root 2. Or square root 2 is about 1.4. So if we did 14 times our 1.4, okay, you could get an approximate number of 19.6. So this is about 19.6. So then in this last one, we do know these legs are going to be the same because we see this 45-degree angle. So this is 45, so isosceles. So now we actually have the diagonal. So how do we go back to the leg? Would be dividing by that square root 2. Okay, so this leg is going to be 24 divided by square root 2, which is like 1.4, right? So 24 divided by 1.4 gives you about 17.1 for those legs. And again, you could do Pythagorean theorem here. Let's take a look at how you do Pythagorean theorem on this one because we don't know the side lengths. Okay, so we knew that the hypotenuse was 24, so we do 24 squared, and then the legs we don't know, but we do know they're exactly the same, so we can use the same variable. So 24 squared is 576, and then we have x squared plus x squared, which means we have 2x squareds. So then we'll divide both sides by 2 to get 288 equals your x squared. Then you can square root. And you'll get 16.97 is the exact answer. Oh, well, an exact answer, but 16.97 rounds up to 17, so approximately the same as what you got here. And if you actually did divide by square root 2, okay, so if you actually divided by square root 2 instead of 1.4, you'd have gotten this 16.97 as well. So let's take a look at generalizing what we talked about today, okay? So this is the idea that happens here, that you have a side times the square root 2 equals the diagonal. Okay, so if you have an isosceles right triangle, you would just take the side, multiply it by square root 2 to get the hypotenuse. Okay, if you have the hypotenuse, to get to the side, you would divide by the square root 2, because you see how this doesn't have the square root 2. So if you have the hypotenuse, divide to get to the side by square root 2. If you have the side, multiply by square root 2. So if we had something like this, so in those last ones, like we said, okay, so if we had 14, multiply by square root 2 to get to the hypotenuse. Okay, if you have the hypotenuse, okay, then you would take the hypotenuse and divide it by square root 2. So here's your summary. Okay, so we know that in a right triangle, a right isosceles triangle, okay, meaning the legs are equal or the angles are 45 degrees, we know that those are similar by angle, angle. So we looked at the 1 centimeter side and found out that the hypotenuse would be the square root of 2. Okay, in that first example that we did. So that triangle looks like this. So you'd have a 1, and a square root 2. Okay, so that's where this is coming from right here. So then that gives us our scale factor. We notice that the legs are 1. We multiply by square root 2 to get the hypotenuse. So if we wanted to generalize that, we could say that the side lengths are x, x, and then the hypotenuse is square root 2x, or x times the square root 2. Okay, so you see that here. So we have x, whatever that is, x, and square root 2 times x. So divide by square root 2 to get the leg, multiply by square root 2 to get the hypotenuse. Okay, so you can kind of see that this just has a square root 2 kind of multiplied in with it. So multiply by square root 2 if you have the side, divide by square root 2 if you have the hypotenuse. So in this one, this other leg here would be 6. So if you've got a 6 here, then this would be 6. And the hypotenuse would be 6 times the square root of 2. Or in this one, we have the hypotenuse. So these legs are going to be the same. And they're going to be the hypotenuse divided by the square root of 2. So that's the generalized form of what you just learned.